Hello, chemistry students. This is Professor Sean McMahon, and this is Chapter 9, Lecture 2 of Solution Chemistry. So in Lecture 1, we talked about defining what a solution is, what a solute is, what a solvent, and we introduced the concept of electrolytic solutions and concentration calculations involving milliequivalents. So today we will continue our discussion of calculations for solutions involving percent concentrations, and we'll continue with that. So as we move forward, since we are talking about solutions and we have previously lectured in week 9, lecture 1, if you're watching these videos through YouTube or my chem course, or just chapter 7, lecture 2 videos, we talked about aqueous reactions and solubility rules. So essentially the solubility is the amount of solute that can dissolve at a given temperature, and it's affected by the type of solvent and the temperature itself. So we can express solubility as the grams of solute. Remember, the solute is what's being dissolved. It's the smaller quantity per 100 grams of solvent. And again, solvent is kind of water is the universal solvent. It's really abundant. So typically when they say 100 grams of solvent, really they're talking about 100 grams of water. So since we're talking about solubility, there are terms used to describe how much solute is actually dissolved in a solution. So if you reach the maximum amount for that given temperature that solute can dissolve in that solvent, again, usually water, it is referred to as a saturated solution. It means you can't add any more. If you do, it will begin to settle out of solution. If you haven't reached the maximum amount of solute, that's considered unsaturated. Unsaturated means there's room for more solute to dissolve and be surrounded by the solvent. Remember in that last lecture, lecture 1 of chapter 9, I talked about solvation, where the solvent surrounds a solute particle. Well, if there's still not a lot of solute dissolved, there's enough solvent to surround it, so that's considered an unsaturated solution. There are conditions where we can exceed maximum solubility limits, because that's essentially what a saturated solution is. You're creating a maximum solubility limit per the given temperature, but you can exceed that by heating solutions up and slowly cooling them down, where you actually have more solute dissolved than you should for the cooler temperatures. Those typically supersaturated solutions, they're very unstable and they can be disturbed quite easily. And in the process, you would see all the solute come out of the solution quite rapidly. So let's first talk about the effect of temperature on solubility. So here is a very general graph. And if you look, you see that it is the amount that can dissolve is dependent on the temperature. So as I increase temperature, we see in general the number of grams of solute per 100 grams of water increases as I increase the temperature. Okay, now we're focusing on the kind of the general concept of solutions where the solute is a salt. And what I mean by a salt, a solid ionic compound, and the solvent is water. So you notice with all of the solutes that they're referring to, these are all ionic compounds, okay? We know that because we have a metal and then non-metals. So again, in general, the solubility of solids in water increases with increasing temperature. And we pretty much see in all of these, it's either exponential or at least linear with an increase in temperature. So what's an example of how we could have a supersaturated solution, for example? Well, at 55 degrees Celsius, the solubility of sodium acetate is roughly 100 grams per 100 grams of water. So if we look under our temperature graph, we see right here at 55 degrees Celsius, there's roughly, it's just shy, 100 grams of solute per 100 grams of water. And if the solute is sodium acetate, we can easily force this to have what is referred to as an unstable environment by taking it and cooling it down to 20 degrees Celsius. So when we cool it down to 20 degrees Celsius, we have gone beyond the maximum solubility limit because we've slowly cooled it down, and it's now supersaturated. So at 20 degrees Celsius, 100 grams of sodium acetate as a solute in 100 grams of water is more than what should be in there. But we tricked it because we've cooled it down. And again, remember, dissolving these salts, you basically have water going in and dislodging the ions and surrounding them. Well, with higher temperatures, there's more kinetic energy, more movement. The water molecules are busier surrounding the solute. Well, when we cool it down, they're moving slower and they can't dissolve as much solute. That's why if we cool it down, we can get a supersaturated solution. Now, like I said, they're unstable, and just a small disturbance, like scratching glass or throwing a little bit more of the sodium acetate, it's called like a seed crystal. If you add just a little bit, you'll get a supersaturated solution. So in this example, you're with a pair of tweezers, we see we're dropping a little seed crystal, and now it's realizing, whoa, here's a disturbance. I have way too much solute dissolved for this temperature, and it comes out of solution quite rapidly. In fact, these links here are active links to YouTube videos where you can see this done in real time on a video. So there really wasn't a need for me to do this, so I just referred you to those videos. So in general, right, solids and liquids, if you increase temperature, you're going to increase the solute's solubility, as we saw in the previous graph, okay? However, with gases, which have a lot of kinetic energy to begin with, if we heat them up, we're giving them more kinetic energy. We learned that with kinetic molecular theory. So now the gas solute particles dissolved in the liquid are going to fly out. So it's the opposite. Increases in temperature decrease the solubility of gases. And we can see this with cold soda pop that has carbon dioxide dissolved. And we see it's fizzing a little bit, but warm soda pop, if we pour it, because there's more kinetic energy, the gas particles are escaping, and we see greater fizzing because the gas particles don't stay dissolved. They're not as soluble in that solvent. So those are the effects of temperature. For solids and liquids, if we increase temperature, I can dissolve more solute. For gases, if we increase temperature, I dissolve less gas because they're going to fly out and escape from the solvent liquid. Now, there is an effect of pressure on solubility for gases. It has no effect with solids and liquids dissolving, because solids and liquids are condensed phases. So we talked about how they don't take enough room, they're going to fit in the median. But realize that gases, because they have a lot of kinetic energy and there's a lot of space between the molecules, if we increase pressure, we're going to increase the amount of gas that dissolves in the liquid. So here's an example. Above any liquid, you can have vapor pressure. So we see these gas particles flying around. So at lower pressure, there's fewer particles above this liquid. So there's fewer particles dissolved in the solvent because they can escape a lot easier because there's more room. You can think that these gas particles, if they get to the surface, it's easier for them to escape into the gas phase and no longer be dissolved because there's a lot of space. If we increase the pressure above a liquid, there's less room. So now the gas particles that are inside, the solute gas particles dissolved in the liquid solvent, it's harder for them to escape. So they stay. They're essentially being pushed down by the pressure, I'll call it atmospheric pressure, above. So the gas particles above are pushing down the particles that are dissolved in the solution, that it makes it harder for them to escape. Now, where do we see this? Soda pop, right? So in a soda can, there's a space above the liquid, and that space has CO2 dissolved in it. So that creates pressure above the liquid that keeps the CO2 gas dissolved in the solvent, in the soda. As soon as I open this can to the environment, and it's no longer a closed system, the CO2 gas particles that are above, that's what vapor pressure is, the gas particles above the solution, as soon as I open this can, the gas particle, the vapors, can escape, which reduces the pressure above the liquid. When the pressure above the liquid is reduced, now the CO2 can escape along with the CO2 that was above the liquid. Funny story is, when I was a kid, I didn't really know chemistry when I was really like elementary school age, and I was kind of a quirky kid, but I would see the 2-liter soda and I'd see this big space and I'd be like, hey, they're trying to rip me off. They didn't fill it up. What I didn't understand was Henry's law. They needed to have that space to have the CO2 gas above the soda so that the CO2 would stay in the soda. So when I opened it up, there'd still be CO2 in there. That's why if you leave soda pop outside, over time it gets flat because there's not enough vapor pressure above it to keep the CO2 in the soda. So it just escapes into the environment. So the other thing on top of the effects of temperature is when we're dissolving solid ionic compounds, right? We have to know our solubility rules. And again, the nice thing is we went over our solubility rules. And again, that was Chapter 7, Lecture 2. If you're in my course right now, it's Week 9, Lecture 1. We went over these solubility rules, which was NAG. NAG is nitrates and acetates, and group 1 alkali metals are always soluble. So insoluble, if it's never, there's no exceptions. The NAG is always soluble. The other trick in those videos I mentioned was SAG. SAG stands for sulfates in group 7. Those are soluble, but there are exceptions. That's where we had castrobare, calcium, strontium, barium. And for the group 7A halides, the PMS, P for lead, M for mercury, and S for silver. Those were exceptions where those would precipitate out. Now, some students say, okay, but we didn't talk about all the other polyatomic ions like chromate, dichromate. So basically, for our course, if I didn't talk about it, right, when I was first introducing NAG, SAG, what I was talking about is what is actually soluble. So if I didn't bring it up, that's because it's always insoluble. So what does that mean? Carbonates, sulfides, phosphates, hydroxides, they're all insoluble. Now, someone might say, well, last lecture, when we were talking about electrolytes, you said sodium hydroxide was a strong base and dissociates completely 100% of the time into ions. So if it completely dissociates because it's a strong base, why are you saying hydroxides are insoluble? Well, sodium is a group 1. And if I have an ionic compound that has sodium in it, doesn't matter if hydroxide, carbonate, phosphates attached to it. As soon as I put it in water, it's going to dissociate into its respective ions. So you have to look at both. You have to look at the cation and the anion to determine whether or not it's soluble. So you can review, again, the NAG, SAG, Castro-Bear PMS, right? NAG stands for nitrates, acetates, and group 1. So here are my nitrates, here are my acetates, here's my group 1. I put in ammonium because it's a +1 charge like group 1. They're always soluble, okay? They're always soluble, no matter what. The SAG stands for sulfates. We have a Castro-Bear exception, I'll talk about that. And the group, because the SAG group, 7A, the halides, and their exceptions, PMS. So the SAG, sulfates are soluble, okay? Sulfates are soluble except Castro-Bear. So Castro-Bear. And I know that acronym doesn't have lead, but lead too. Lead is another time when it's insoluble. Then with the SAG, group 7A, the halides, PMS, the lead, mercury, and silver, you got your lead. It's actually lead 2, mercury 1, and silver. And again, if it's any of those other ions that I had earlier, it means it's insoluble unless it's with one of these. So hydroxides, sulfides, phosphates, carbonates are all insoluble, right? So I could literally just write that right here for you. They're always insoluble. So why do we need to know this? Well, remember, with reactions that are aqueous, right? Like this reaction, we have silver nitrate, potassium chloride, yielding, producing silver chloride and potassium nitrate. What's more important is, for our topic right now, is this is aqueous. That means that these are dissolved in water. Now the silver chloride precipitates out. This is a double displacement precipitation reaction. That's one of the 5 basic types that we talked about. With silver chloride, the reason why this is insoluble is, remember, group 7A, PMS, S for silver, chlorides are soluble unless silver is around, and then it precipitates out. What we're doing here is we're writing out the full chemical reaction, and we're writing it in molecular formula. So it's called also the molecular equation. However, in reality, with solutions, now that we understand solubility rules and solvation and the process of dissociation, we have to realize if it's aqueous and it's a soluble ionic solid, the ions are actually separated. So we did this when we were kind of trying to predict products where we would separate the nitrate and the silver and the potassium and the chloride, and I would say crisscross applesauce. You guys might remember that, okay? Well, I was prepping you because now we want to write out what's referred to as either the total ionic or the complete ionic in a balanced chemical equation. So when we see silver nitrates, we know nitrates are always soluble. So that means that the silver ion, and I have to include charge, is actually separated from the nitrate ion. When I look up potassium chloride, it says aqueous, and I know that the potassium is always soluble because it's group 1. So I separate the potassium ion from the chloride. When I get to the product side, what I notice is that the silver chloride precipitates out. Now, why? That's because the chloride and silver ions have a stronger interaction. So that's solute to solute interaction between silver and chloride is greater than the interaction between the solute to solvent. So basically chloride likes silver more than it likes water and being surrounded by water. So it precipitates out. And we write solid. So that means it's no longer in separate aqueous ions. So we write basically, when we're writing out complete ionic equations, solids, liquids, and gases, you do not separate ever. They're always in molecular form. And if you have a covalent molecular compound and it's aqueous, you wouldn't separate that into ions. So remember, I said this with the electrolytes, like your sucrose. If I threw this solid, it would dissolve, but it would not separate into ions. These are ionic compounds because I have charges. Here's a cation, here's an anion. Okay. What I also notice is a potential product, potassium nitrate, in the molecular equation. I get that formula from the crisscross between the positive potassium and the nitrate. And I write out the neutral formula so that I can balance this full chemical equation. But with the total ionic, what I need to do when I'm doing the total ionic is I need to separate the aqueous salts, right? The soluble ionic compounds are going to be separated ions. So I see that potassium is separated from nitrate. Why is that? Group 1 and nitrates are always soluble. Now, why is that important? Well, from the total ionic or complete ionic reaction, we can eliminate on both sides ions that are simply just staying dissolved, floating around and not doing anything. Those ions are referred to as spectators. They're spectators. They're watching the other ions come together and yield some type of product. So those spectator ions, we're going to cancel those out and come up with what's referred to as a net ionic reaction. The net ionic reaction is the true reaction. It's kind of like you have your gross pay before taxes, then they tax you and take everything out and you net far less. Well, that's what we're doing with these total ionic equations. We're taking everything and we're cutting out, not the taxes, but the spectator ions. So how do we do that? Whatever ion is on both sides, we eliminate. So if I look, I have nitrates separated on both sides of my potassiums. So I cross that out, and what's left? The actual reaction. The net ionic equation shows what ions are involved in forming the precipitate. And it's the silver ion. Remember, I got the silver ion when I dissolved silver nitrate because nitrates are always soluble. So that dissociated and had this free-floating silver. Remember, I got this chloride ion because potassium chloride, right? Potassium, group 1 is always soluble. It's separated. Now I have free-floating chloride. But when the silver and chloride see each other, boom, they come together and they produce silver chloride as a solid. And that's my precipitation. And I would see a white precipitate come out into the solution, right? So basically you're taking a test tube that has silver nitrate, a test tube that has potassium chloride, you pour them into each other, and then in the mixture, you get a white precipitate, and that's your solid. And then the potassium and the nitrate ions are just floating around, not doing anything. But we want to write out what the heck, what ions form this precipitate. And we do that using net ionic equations. So it shows the species that are actually doing something. They're not just spectators, right? So for the next sample exercise number 2, I have like numerous examples, okay? And I'm making it challenging. I'm having you look at the nomenclature, the name of the compound. Then I have you predict the products. And then you have to determine which one is insoluble based on those solubility rules. So we've already kind of introduced this with the 5 basic types of reactions, double displacement, but now we're revisiting it because we're expecting more. So iron 3 bromide. Why iron 3? Transition metal. Has more than one charge. What's the charge? +3. So that's bromide. It's a -1. Why? Halogen. Plus, and actually, you know, I'll leave that up for right now. Potassium phosphate. Phosphate is an oxyanion, non-metal, one of the 5 big 8s we talked about. It's on the 4, so it has 4 oxygen. So it's PO4 3-. Now, why am I writing this out? Well, my reactants are this and this. So I would do the crisscross to figure out the formula. And the reason why this is aqueous is because halides group 7A are always soluble except PMS, which stands for lead, mercury, silver. This is iron. So this is aqueous. So this is free floating. Plus potassium phosphate. So we would crisscross K3PO4. Why is this aqueous? Well, potassium is always soluble. It's group 1. Now what do we need to do? We need to predict products. How are we going to do that? Okay, I'm going to rewrite this. Fe3 plus Br minus K plus PO4 3-. So what are we going to do? We're going to crisscross. So one product is iron 3 phosphate because they both have a 3 plus and a 3-. It's a 1-to-1 ratio. And then the other one is the potassium bromide. There's a plus and a minus. So I have KBr. Now I have to see if an actual reaction took place. Well, with the potassium bromide, I know potassium group 1 is always soluble. This is aqueous. So there's no reaction. However, phosphates, they're not part of that acronym NAG, SAG, Castro-Bear, PMS, because phosphates are always insoluble. So that's my solid. So in this double displacement reaction, right, because that's what this is, 2 salt solutions combining to form a precipitate, right? Compound, compound, new compound, which is a precipitate, new compound. I just wrote out my molecular equation. Now, what do I have to do next? I have to balance it. So how do I balance it? Well, first I would do what? Metals, 1 iron, 1 iron. Then I would go to potassium. There's 3 here. There's only 1. So I'm going to put a 3 right there. Now I would go to nonmetals. Well, I have 3 bromides on the product side, but I have 3 bromides in the reactant side. So I'm okay there. I have phosphate on both sides. I'm not going to split it up. 1 phosphate, I'm done. So there is what we did in chapter 7, right? In the 5 basic types of reactions. But now we're also incorporating the nomenclature and tying it into our solubility rules. So this is a lot of review. And there's the equation, okay? But this is my molecular equation, right? This is the chemical equation. I want you to also do the complete ionic and the net ionic. So what do? Wherever the ionic solid says aqueous, I'm going to separate it to its respective ions. Solids, liquids, and gases, I do not separate. So my total ionic, iron 3, remember in the beginning, that's how I figured out the formula. Bromide, it's Br minus, but I need 3 of them to make it neutral. So you need the correct coefficients and the correct charges, and you have to have the correct phase. So there's quite a bit going on here. Then I have my potassium phosphate. Potassium's a +1. We did that earlier. And I need 3 of them because phosphate's -3 because we crisscross. But now it's 3 separate. They're not, the potassium ions aren't bound to each other. They're separate ions, each of them surrounded by water. And there's 3 of them, okay? And then the 1 phosphate. On this side, the solids together, but now I have the 3 potassium bromides. So you can think there's 3 of these potassium bromides. So I'm going to have 3 potassiums, and then when I split this in half, I'm also going to have my 3 bromides. This is total. What do we have to do next? Net ionic. Okay, so how do we do the net ionic? We have to eliminate the spectator ions. How do we do that? Whatever ions are on both sides, they haven't done anything. They didn't produce anything. So I have 3 bromide here, 3 bromide here. It hasn't changed. It's not involved in a reaction. It's an ion that's happy to be soluble in water. So because it's a spectator and it doesn't produce a solid, liquid, or a gas, I'm going to eliminate it. That was kind of fun. Now I go to potassium. There's 3 here, there's 3 here. That's because potassium doesn't want to be bothered. It wants to stay, it likes water. It likes to be surrounded by water. So it stays dissolved and I cancel. Well, that's perfect. What does that leave me? My net ionic equation. To produce a solid of iron 3 phosphate, it required the iron 3 cation and the phosphate anion. When those saw each other, they had a greater attractive force amongst each other in that solute-solute interaction than they did for the water. So they precipitate out. Cool, huh? So go ahead and pause, try to do this one. Now, I'm not going to break this one down like I did for the first one. I'm just going to show the answers, okay? But I will help determine the formulas, right? Ammonium is a +1 carbonate, CO3 2-. Remember, the oxyanions of 5 big non-metal eights I talked about, carbonate was one of them. It has 3 oxygen because it's not on the 4. Copper 1 sulfate. So now what are we going to get? Well, ammonium carbonate, or again, if I crisscross, because of the charges, I need 2 ammonium per 1 carbonate. If I crisscross here, I need 2 copper 1s per sulfate. Now, when I group the ammonium with the sulfate, ammonium's +1, sulfate's 2-, so I need 2 ammonium. When I group the copper with the carbonate, this is copper's +1, this is 2-, I need 2 copper 1s. When I go to my solubility rules, why is this aqueous? Because carbonates are typically insoluble. Remember, ammonium has a +1 charge like what group? Group 1A. And group 1A, according to NAG, is always soluble, so is ammonium. So this ammonium is going to split up. It doesn't matter if it's in a solid with phosphate, hydroxide. As soon as I throw it in water, boom, dissociates. Sulfates are soluble except Castro-Bear and lead. It's actually slightly insoluble with copper, but for this example, we're going to say it's soluble. So because the copper 1 is not one of the exceptions for sulfate. However, on the other side, carbonate and copper come together, and carbonates are insoluble. They're not part of that NAG, SAG, Castro-Bear, PMS. It precipitates out. And then all I have to do is balance the equation. And in this particular case, it's balanced for you. I'll let you determine if it's balanced or not. But now what do I have to do? I have to separate the ions to write out what? The complete ionic equation. So what do? 2 ammoniums. I needed 2 because carbonate's a 2 minus. 1 carbonate. They're dissolved. As soon as I throw that salt in, the copper 1, there's 2 of them because sulfate has a 2 minus. They're separated. But now that these can swim around and come in contact with another, these 2 are like, wait a second. I'd rather be with you than surrounded by water, and they produce the precipitate. We have this as aqueous because ammonium in the product side, we look at the ammonium sulfate in the product side. The reason why this is aqueous is ammonium is like group 1. It has a 1 charge. It's always soluble. So it keeps separating. So for the net ionic, what do I need to do? I need to cancel out spectators. Well, the ammonium's not doing nothing. Neither is the sulfate. What's left? The 2 copper 1s and the carbonate, producing my solid. So calcium sulfide and tin 4 acetate. The calcium sulfide is slightly soluble, okay? So when I look, I have aqueous, Y is at a 1-to-1, calcium's 2 plus, sulfide's 2 minus, tin 4 acetate, tin, or in this case, stannic, tin 4 acetate, C2H3O2 minus, crisscross, I need 4 acetates. Acetates are always soluble. Okay, on this side, acetates are always soluble, but what do I have? Sulfides tend to be insoluble, and tin is a heavy metal, it precipitates out. So this is my molecular equation. What do I need to do? Total ionic. 2 calcium, 2 sulfides. Why? Because I had to balance it with the 2s. 1 tin 4, 4 acetates right there. Why? Crisscross. I need 4 of these. On this side, 2 calcium, 4 acetates, tin 4, and sulfide. And how do I get that formula? Tin 4, sulfide. You would think crisscross, which would be SN2, S4, but we want the simplest formula, so we divide by 2 and we get SN2. So now I need to eliminate spectator ions. How do I do that? Well, there's 4 acetates that don't do anything, and there's 2 calciums that don't do anything. So what's left? Tin 4 plus the 2 sulfides produce tin 4 sulfide as a solid. That's my net ionic. So that's, quite a bit there. But honestly, we've already covered these topics in the double displacement reactions and aqueous reactions discussions in chapter 7. So we're just building on that. Now, why is that? Well, when we talk about concentration and solution concentration in chemistry, most of the homogeneous mixtures are salt solutions. We take ionic compounds, we dissolve them in water, right? Now, we sometimes hear terms dilute. Dilute just means I don't have a lot of solute dissolved. We hear, man, this is really concentrated. Another expression could be it's saturated. Dilute would be unsaturated, right? So this is just terminology you have to get comfortable with, right? Concentration is essentially the amount of solute, and I'll write that. Concentration is the amount of solute per solution, right? So I'm dilute if I don't have a lot of solute. You can think of it as unsaturated. I'm a concentrated solution. There's a lot of solute for that solution, and that would be saturated. So there's ways to actually give, rather than just terms. Again, with the saturated and unsaturated, we had the tables where we can use quantitative analysis, but dilute and concentrated, those are qualitative terms. Let's actually do a calculation and make it quantitative. So 1 is referred to as mass percent, and they do mass to mass because they're comparing the mass of the solute to the mass of the solvent. And it's typically the number of grams of solute per 100 grams of solution. So how do you get the mass of the solute? You just weigh the solute. And then the mass of the solution, remember the solution is 2 components, solute and solvent. So you have to add up the total. So I like to tell people, remember percents, because this is a mass percent. I could have just written mass percent. Percent is just what? Part over whole times 100. So the part is the solute. The whole is the solution, but that's the solute and the solvent. And I times it by 100. So mass percent. A student prepares a solution from 5 grams of sodium chloride dissolved in 97 grams of water. What is the concentration in mass to mass? So remember, you're doing part per whole times 100. That's any percentage. So first you have to figure out what's the part. The part is a smaller quantity. The smaller quantity is the solute and is the 5 grams of sodium chloride. The whole is the solvent, the larger quantity, plus the solute. The solvent is the water. Why? There's more of it. But for the total whole, I have to add the water mass and the solute mass to get the mass of the solution, because it's solute plus solvent. So 5 grams divided by 5 grams plus 97 grams times 100. Okay. Now, a lot of people get tricked up, and I want to clear something here. For the whole, remember, this is my solute plus my solvent. This is a good time to review. Yes, significant figures. This goes to the tenths. This goes to the hundredths. When I add, I go to the least precise, which is why the 102 only goes to the tenths. Now, in my numerator, because this is a quotient, what do I mean by quotient? I use division. I no longer use the precision. I use the number of significant figures. So on the numerator, there's 3. In the denominator, there's 4. So my final answer should have 3 sig figs. So the answer for this solution, mass percent, is a 4.90 mass percent of salt in this solution. Now you can change it. You can add more salt and change the percent. You could have a 5% salt solution, a 10%, a 15%. You can do that because they're not chemically bound. You're just adding solute that dissociates and dissolves. That's why this is a mixture and not a compound, because I could physically separate these through distillation or evaporation. They're not chemically bound. Okay. So now it's starting to come full circle. We're taking everything we learned in both lecture and lab. Let's do some practice. Calculate the mass percent of a solution containing 27.5 grams of ethanol and 175 mils of H2O. Now I give a hint. The density of water is 1 gram per mil. I do not have to give that hint. So someone might say, well, wait a second. They're saying mass percent, but this is in milliliters. I brought this up earlier in lecture 1 of chapter 9. Water is 1 gram per mil. That's what's so nice about density, and it's the only density you need to know. And since water is a universal solvent, right? When we think of chemistry, we're thinking water is a solvent until you get to organic, but for now, so I can just say this is 175 grams. So now, which one's less, 27.5 or 175? 27.5. So the ethanol is the part. The 175 plus the 27.5 is the whole, because this is my solvent. This is my solute. So here we go. Mass of solute divided by mass of solute plus solvent, convert using density, the 175 mils to 175 grams, part over whole, the 27.5 over 27.5 plus 175. The reason why I'm underlining the 2 is because the 175 only goes to the 1's place, so this goes to the 1 place. So really, this is 3 sig figs on the bottom. I'm just trying to reduce round off error with that 0.5 there. And then the top has 3 sig figs. So 27.5 divided by 202.5 times 100. When I take into account 3 sig figs, it gives me an answer of 13.6% alcohol, which is equivalent to, what is that, 27.2 proof. That's a weird proof. 27.2 proof. Sean, what are you doing? People like 4 or 80 proof. Okay, anyways. So what we can do is we can use these percentages, like, for example, if there's a solution that says it's 23.2% alcohol by mass, let's make this a ratio, a conversion factor. Really, this is a nice thing about percents and concentrations. I can now say, well, if it's 23.2% ethanol by mass, that means there's 23.2 grams of ethanol per 100 grams of solution. Or you can flip it, and that's very powerful. Well, now let's take a look at sample exercise 3B. A soft drink contains 11.5% sucrose by mass. So here's my solution. The sucrose is a solute. Why? It's a lesser quantity. It's only 11.5%. What volume of the soft drink in milliliters contains 85.2 grams of sucrose? Wow, okay, this is a lot. I'm looking for milliliters. That's probably why they're giving me density, because I'm starting with grams. Now, a lot of people might say, well, why don't I start with the 11.5? Remember, this is a ratio. You should be thinking the 11.5% sucrose by mass is really 11.5 grams of sucrose per 100 grams of soft drink. That's what you should think. The soft drink is a solution, and its density is 1.04 grams per mil. So there's 1.04 grams of soft drink per mil of soft drink. But I want to know how many mils if I have 85.2 grams of sucrose, right? So how do I do that? I have 85.2 grams of sucrose. I know that there's 11.5 grams of sucrose from this percent per 100 grams of soft drink, but I'm going to flip this because I want the grams of sucrose to cancel. Now I have grams of solution. The density is there's 1.04 grams per mil of solution. So I can flip it, and then the 1.04 grams of solution cancels with the grams of solution unit there. I'm left with milliliters. It's 712 because I have 3 sig figs, 3 sig figs, 3 sig figs. Yep. Well, like all percents, there could not just be a mass to mass, right? Because mass to mass is really good if I dissolve a solid into, let's say, water. But what if I dissolve a liquid in water, right? So we don't use the term soluble with liquids. We use miscible. So what if I have a miscible liquid that I dissolve in water? Well, it doesn't make sense to do a mass to mass percent. So instead, we're going to do a volume to volume percent. It's still part over whole times 100. We just change the units to milliliters instead of grams. So a 7% volume to volume solution basically contains 7 mils of solute per 100 mils of solution. That's what it means, right? So because if you went 7 divided by 100, you would get 0.07. But remember, to get percent, I need to multiply it by 100. The reason I write it right here like that is if I want to put this as a conversion factor for problem solving, I can just do that. Sample exercise 4. What is the volume percent? So look, milliliter per milliliter, part over whole times 100, right? But bromine in a solution prepared by dissolving 12 mils of bromine in the solvent, they're even telling you the solvent. You don't even have to think about it, because normally you'd be like, this is bigger, this is smaller, this bromine, and it's a diatomic, because remember, bromine, it's Sir Brinkelhoff, it's one of the 7 diatomics. It's smaller, this must be my solute, and then the carbon tetrachloride must be my solvent. Now, the reason why the bromine can dissolve in carbon tetrachloride is bromine is nonpolar. Right, here's bromine. Lewis dot structures. Oh man, I love how it all comes together. Here's bromine. That's symmetrical. That's nonpolar. Like dissolves like. It will not dissolve in water. Okay, why? Water is polar. So we're using carbon tetrachloride. And I'm going to do lines instead of dots because it's faster. But look at carbon tetrachloride, it's symmetrical, it's nonpolar. So they dissolve in each other, which means they're miscible, but because bromine's a liquid. But now what we're going to do is we're going to figure out the volume percent. How do we do that? Well, volume of solute over volume of solution. If the solvent and the 12 mils of solute make 250 mils of solution, they didn't say 250 mils of carbon tetrachloride, because then you would have to add the two. They just said 250 mils of solution. So this is easy. Put the 250 mils, put the part 12 mils of bromine, times it by 100, we get 4.8% bromine. Why? 12 has 2 sig figs, 250, this trailing 0 does not count because there's no decimal. And we don't know the precision beyond the tens place, not the ones. Let's try another one. Let's use the percent as a conversion factor, like we did earlier with the mass percents. Calculate the amount of solute in milliliters needed to prepare 225 mils of a 15% isopropyl alcohol solution. So 15% means there's 15 milliliters of isopropyl alcohol. I'll just do ISOH because OH means it's an alcohol group per 100 mils of solution. That's my conversion factor. So if I want 225 mils of solution, how much mils in solute do I need? Well, 225 mils of solution, I put this conversion factor of 15% part over whole. It's a conversion factor. 100 mils gives me 15 mils. The mils of solution cancel. I get mils of isopropyl alcohol as a unit, and it's 33.75 mils of isopropyl alcohol, but the 15% is only 2 sig figs. That's why I underlined it. So I got to round up to 34 mils of isopropyl alcohol. So I need 34 mils of the isopropyl alcohol, and I bring it up to volume. So I add enough water to bring it up to 225 mils to get a 15% solution. So basically you would have a volumetric flask. You would add your 34 mils of your isopropyl alcohol, and then you would fill your volumetric flask up to 225 mils with water. First, you would dissolve it and then bring it up to volume. You can imagine if there's a mass to mass percent and a volume to volume, well, It makes sense if we're dissolving solids in a liquid that we don't always have to change the milliliters to grams using density to get a mass to mass percent. We can, I mean, that's perfectly fine, but we can just do a mass to volume. It's still what? Part over whole. And what's the part always? The solute. That's what concentration is. How much solute dissolved in solution? That's the whole purpose of quantifying this, because we want to know how concentrated is this? How much solute? So part over whole times 100. So what do we use? If it's mass to volume, the solute is in grams and the solution is in milliliters. So a 5% mass to volume percent solution contains 5 grams of solute per 100 mils. The reason why I did 5% is in intravenous solutions, right? IVs, they have 5% glucose. That means there's 5 grams of glucose per 100 mils of IV. So calculate the mass volume percent for the solute in 75 grams of sodium sulfate in 250 mils of a sodium sulfate solution. So this is my solute of 75 grams. My solution's total volume is 250 mils. So how do I get the mass to volume percent? Part over whole times 100. So put grams of solute over milliliters of a solution times 100. 75 grams over 250 mils times 100 gives me, I want 2 sig figs because 75 is 2, 250, again, that trailing zero doesn't count. 2 sig figs, I have to put a decimal here because there was some rounding to show that there's 2 sig figs, because if I just wrote 30, that's 1. I put the decimal to say, to the precision of the ones place, my mass to volume ratio of sodium sulfate is 30% of this solution. I could have a different solution. I could have one that's 20, but if this is the one I'm making, that's the percentage. What about, can I calculate the amount of solute in grams needed to prepare 450 mils of a 2% mass to volume potassium hydroxide solution? What is a 2%? Part over whole. Well, what's the part? The solute's mass. So there's 2 grams of potassium hydroxide per, it's a percent, 100, what's the unit? V, volume, milliliters. So there's 2 grams of potassium hydroxide per 100 milliliters of solution. That's a conversion factor. How much solution do I want? 450 mils. So 450 mils, I put on the bottom 100 mils, the mils cancel, right? On top is the 2 grams potassium hydroxide. I need 9 grams of potassium hydroxide. So again, how would I do that? I'd weigh out, 9 grams of my potassium hydroxide. I would bring it up to 450 mils of water, and then it would separate into its respective ions, because potassium hydroxide is one of the 6 strong acids, and it completely dissociates, and it would be a strong electrolyte. Yep. C. A patient receives 100 mils of a 20% mass to volume mannitol solution every hour. Oh, allied health measures, here we go. This right here is exactly the type of calculations you'll be doing when you take pharmacology and things like that. So 100 mils of a 20% solution of mannitol every hour. How many grams of this drug or this substance does the patient receive in 12 hours? Okay, so there's a couple things. Patient receives 100 mils every hour. So I get 100 mils of this solution per hour. And it's a 20% solution. What does that mean? There's 20 grams of mannitol per The unit for the solution is it's a volume, so per 100 mils. Well, how many grams do I get, right, if I want 12 hours? Well, okay, set it up. 12 hours. Every hour, says it right here, every hour, there's 100 mils. So hours cancel. I want to get rid of mils of solution because I want grams of mannitol. Well, per 100 mils of solution, there's 20 grams of mannitol. So the patient's getting in 12 hours for this 20% solution where they're getting 100 mils every hour, 240 grams of mannitol. Pharmacology calculations. All allied health majors pretty much have to learn how to do this. Yep. This is probably one of the most important lectures for anyone going on to any type of facility where you have to do pharmacology calculations right here. This is super important. And along with the molecular geometry because of all the biochem and organic that you have to take. So what can we do with all these percents? We can put them in unit factors. So if I tell you I have a 4.9 mass to mass sodium chloride solution, it means I have 4.9 grams of sodium chloride per 100 grams, and I can flip this. What it also means is of the 100 grams, remember, I'm subtracting the 4.9 grams of solutes, and I'm left with 95.1 gram of solvent. So I could even say, you know what? Of this 4.90 sodium chloride solution, if I have 4.90 grams of sodium chloride, excuse me, that means I needed 95.1 grams of water. Or I need 95.1 grams of water to bring this 4.90% sodium chloride solution to a total of 100 grams. So I can create 2 parts over whole. Remember, the whole is the solute and the solvent. So one part could be the solutes, but what I want to show people is one part can be the solvent too, even though it's the greater quantity. So I can use those unit factors to help me figure out not just how much solute, how much solvent. And you've already seen we've been using the volume to volume and the mass to volume ratios. So I really like percents. Chemistry, we don't do a lot of percent concentration, I'll be honest. This is primarily geared towards allied health majors. So, you know, anybody going into the healthcare field, if you're going on to biology, they use a lot of the percent calculations. So this lecture is for you. Right? If you're allied health or bio, right? Chemists primarily do molarity, okay? And that'll be next lecture because this lecture is getting a little bit long. So we'll save molarity for next, but all of these calculations are to tell me concentrations. And what we see is, if I tell you I have a 15% mass to mass potassium chloride, there's 15 grams of potassium chloride per 100 grams of solution. And I can make a conversion factor, and I can flip it. If I have a 12% volume to volume, there's 12 mils of ethanol per 100 mils of water. I can make a conversion factor. 5 mass to volume glucose, 5 grams of glucose per 100 mils of solution, right? So in the 2 top ones, if this is mass to mass, if 15 grams of the solute is potassium chloride, and the total solution is 100 grams, I could also say there's 85 grams of water per 100 grams of solution, right? Because 85 plus 15 is 100, the total. Just like with the 12 mils of ethanol per 100 mils of solution, well, then I can say there's 88 mils of water per 100 mils of solution. It's a little bit trickier here, so you tend not to get that. because the grams and the mils aren't as easily interchangeable. But if you have mass to mass or volume to volume, you can do that. So what mass of a 5% solution of dextrose, which is basically glucose. Oh, look, I even got a picture of an IV. Excellent. Look at that. Contains 25 grams. So you want grams, 25 grams of dextrose I want. How do I do that? Well, there's 5 grams per 100 grams of solution. So I need 500 grams of IV, basically. That's what I need. So what mass in grams of solution contains 50 grams of nickel 2 acetate in a 6.5% mass to mass solution? So nickel 2, transition metal, we need to have the stock system Roman numeral to say the charge. Acetate, 2 minus, we're going to crisscross. So I have 6.5 grams of nickel 2 acetate. So I need 2 acetates per nickel per 100 grams of solution, right? But I want 50 grams of the nickel 2 acetate. So how much solution, what mass in grams of solution do I need? Well, I need 50 grams of nickel 2 acetate, and there's 6.5 grams of nickel 2 acetate per 100 grams of solution. This cancels. 50 times 100 divided by 6.5. I need 769 grams of solution. So basically, I would weigh out 50 grams of the nickel 2 acetate, and then I would put it on a scale and add enough water to bring it to 769 grams, and then dissolve it. So last but not least, how many grams of solute are dissolved in 20 mils of a 3% mass to volume calcium nitrite solution? That's nitrite, not nitrate, because it's not NO3, it's NO2, right? The reason why there's 2 is calcium's a 2+, nitrite's -1. If it's 3% mass to volume, it's 3%, 3 grams of calcium nitrite per 100 mils of solution. How many grams of solute are dissolved in 20 mils? 20 mils, well, there's 100 mils per 3 grams. So 20 times 3 divided by 100 gives me, I need 0.600 grams of calcium nitrate. So that is the end of this lecture. Next lecture, we'll talk about what chemists are more familiar with, molarity calculations to determine concentration. Again, this lecture, our focus was discussing things such as the solubility of solids, liquids, and gases in solution, how temperature affects it, and for gases, how pressure affects their solubility. We also talked about the calculations for concentration of mass to mass, volume to volume, and mass to volume. And again, the other way of quantifying it will be molarity, and that will be covered next time. So thanks so much for watching. I appreciate it, and I'll see you next time.